I guess I'll go over the solution now. So these are sort of the values on my VM that I had as far as the addresses for each of these methods are concerned. So for me, uran48 was located at this address, and system was located at this address. And I actually passed the /bin/sh string through the input string, and that was also located on the stack in the 7E space. So if you reference your stack diagram, I'll actually walk through sort of why that stack diagram is the way it is. So, here, and here. So first of all, I guess kind of use the Perl script to output the solution. So buffer, actually, if you notice in the boverflow.c source file, it's a car array of 5 bytes, but since it has to do 4-byte alignment, it'll actually allocate 2 spaces on the slot, right? So it becomes 8. And so you get these essentially 2 4-byte spaces on the stack for buffer. And then followed by that, we have to have an additional value for the Kali saved register, which is R11. So if you disassemble stage 1 in GDB, you'll see that both R11 and the link register are getting pushed onto the stack. And so the R11 comes right after the buffer. And then following that, we need, as per the stack diagram, we need the link register. And in this case, since my ERAD48, the specific instruction for loading into R1 and R0 was located at 76F28E56. I have to actually add 1. And so, and I have to also write it in little endian format, so you kind of have to reverse the byte order for the address here. So you would put 578E F276, and then you concatenate that with the address of your string, which in my case was, this is an older one. So for me, the string was located at 7EFF6E8. And so I'll have that. And then followed by that, we essentially have R1, which is actually not used by the system syscall. It only expects 1 argument in R0, so we can put some junk in there. And also because ERAD48, that line does a load register double. So you have to have 2 values there, so it can load those 2 values into R0, R1, because they're also updating the stack pointer there. And you'll also see in ERAD48 there's a stack pointer -12, which means it's moving 3 4-byte spaces on the stack, and which is why you sort of need to include junk values there. So the first junk value is the R1 value. The second one is any junk value that you want, like IJKL in my case. And followed by that, we actually need the system address. So the address for the system call, system function is actually, for me, was located at 76F2D768. So you have to add 1 here again. So wherever there's a branch with link occurring, where it takes the address from the link register and puts it into the PC, you have to add 1 as the least significant bit. So you can't see that. So that's actually a 6-9 there. So instead of a 6-8, I just added 1. And again, this address has to be in little endian format. And once you have the system syscall, then I actually put the shell string and pass that through onto the stack. And so once I have this, Alright, so once I have that, I can go into GDB buffer overflow, and we'll actually step through and see what's happening. So I usually put a breakpoint on state 1, and I'm also going to put a breakpoint at the last instruction there, just so we see that branch with link occurring. So now if I say run so first I hit the stage 1 code. As you can see, it's already advanced itself. Then I hit continue. So right now I'm at the last instruction in stage 1. And if you actually go to examine the stack, you can actually see I inserted 3 ABCDs. So you can see that's ASCII encoding. So it's X41, 42, 43, 44, and it occurs 3 times on the stack. And then I had fed the value in little endian, and so you can see it's actually, GDB shows us the big endian format when you do memory, examine memory, so that's why you're seeing it as the straight up address, 76. So this is our address for ERAN 48, and we can actually disassemble ERAN 48 to see that address, right? So you have 76F28E57, and that's going to be, it's actually 56, so it's going to land us right here. So when I do step I, so right now I'm in ERAN 48. So now we can actually step I and then look at what's in R0 and what's in R1. So R0 should have the address of our string, and one way to verify that is you just say examine/string $R0. So apparently my string is not there. Let's see. Actually, I think I might turn it on. If I actually check the stack, so I'm looking for 2F2F, which is this guy. Okay, so my address is off for the string now, so I'm going to have to redo my string. But essentially, all you're doing here is once you have the string address, you should be able to actually load the address of the string into R0, and then you'll get the junk value, which in my case I use like EFGH. And then I add another junk value because the stack pointer is being decremented by 3 stack spaces instead of just 2. So you'll have R0, which is the address of your string, R1, and then one more value. So I used EFGH, IJKL as the junk values so that the stack pointer would adjust itself. Following that, we're going to have the address of system, and the system actually gets loaded into PC, and R0 is going to have the address of our /bin/sh string, and you're going to pop a shell. In my case, it's not going to work because the /bin/sh is not in the correct location on the stack. So. Okay, so now I'm using Dave's address from the memory, so it seems to be pretty static as compared to the stack.
Yeah.
And so now if I actually continue, I get a shell, so so it'll start running with the same privileges as whatever this process was running in. So. Back to GDB. So I haven't been able to make this work without GDB yet. So the addresses change if you're not using GDB. The only thing I know that GDB does is turn off randomization. But yeah, so if you have any suggestions, let me know. Okay, yeah, works. All right. So the issue was that the stack kept moving. No, so Dave actually found out a location in memory where the same /bin/sh is, but it's not a stack address. Okay. So that's the trick. Nice. Thanks, Dave. So. Did everybody get that? Close. Close? All right. Well, close enough, so. The next stage I would have liked to do is format string. But I didn't actually have a chance to do that. So now that you all are lead actors, right, and we know how to do assembly, we know how to write C code. Do we really know what happens when we compile our C code, right? There are certain things that we assume happen for us, right? So there are certain optimizations that are built into GCC, and this is cross-platform. And so I'd like to say this, however, with great compilers comes great responsibility, because you have to know sort of what code is being generated on the assembly side, especially on embedded systems, because embedded systems are used in a lot of safety applications, a lot of very critical applications. So it's very important to actually understand how the C code gets compiled down into assembly. So with that, here's an example from Professor Dave O'Halloran's book, Computer Systems. So usually the compiler knows best, but in this case, can you guys tell me what's wrong? So actually, let me start sharing. Anybody know what's wrong with this piece of code? So are function 1 and function 2 the same? But would you get the same value in A from both function 1 and 2? Exactly. So if you were to pass in the same pointer, right, for both A and B in function 1 and function 2, function 1 would possibly give you 4 times the value of the value that was passed in to both A and B, but function 2 would give you 3 times the value, right? So they're clearly different. So when the compiler compiles this sort of C code, right, an ARM, it would rather use the inline barrel shifter, right, and do it this way. But if you were to use just plain C and write the code yourself, if this were to get optimized in this way, then you would have different results. And so if you guys are more interested in more evil C, check out this link in your training. So some of the optimizations that GCC does for you is things like dead code removal. It's essentially code that never gets run in any of the control flows, never reaches that piece of code. And so GCC is pretty good about removing such code. So one way to help the compiler decide that is to use like if-defs. So if you use if-defs, right, it's pretty easy for the compiler to check the variable state and see if it's ever going to get run, and then remove that piece of code if that define never is set. And another one is induction variables and strength reduction. Induction variables are variables that always increment in fixed amounts, or increment or decrement in fixed amounts inside of your code. And generally, strength reduction means that instead of incrementing, decrementing by multiplying, you use a weaker function like addition, right? And additions can be a little bit more optimal than multiplication, for example. It takes less cycles. Another one is called loop unrolling. So loop unrolling, I'll go over an example later, is where you actually, instead of running a for loop and running the same piece of code, and writing just a short piece of code, loop unrolling actually increases the code size. But what you do is you take the number of times you loop and divide it by an integer, but you repeat that same piece of code that many number of times, and it actually helps the it actually reduces the number of branches. So we'll look at that example a little bit later. Another one is function inlining. So inline functions, if you're probably already familiar with that, is it replaces whatever function call you make in the code with the actual contents of the function in line with the rest of the code. So this reduces the number of branches because it doesn't have to branch to the function and then come back. And it helps the branch predictor, sort of. So here are some ARM-specific optimizations. You've already seen the barrel shift. It's more optimal to use the inline barrel shifter to operate on registers than to actually do multiplication. So another one is use of conditional execution. I'd mentioned this before, where if you use the conditional mnemonics on the instructions, it also reduces code size and the number of execution cycles. It's actually not execution cycles. What I meant to say there was it increases your throughput because the ARM processor can optimize for the pipeline, essentially. Another one is countdown loops. And instead of doing from I equals 0 to I is less than n, where n is some big number, you do I equals to n and then decrement down to 0. And that's because when the loop is translated into assembly, instead of getting an add, compare, and branch, you actually get a conditional branch along with the subtract instruction. And the conditional branch, as we all know from above, tends to improve your branch prediction, and it's more optimal that way. So, and another thing is, since ARM is 32 bits, it's always good to use 32-bit data types as compared to non-multiples of 32, because misaligned memory accesses can be very costly. Another one to avoid is divisions. As we all know, the Cortex-A profile doesn't have any integer division operation, and so it's best to avoid division as much as possible. It's a very expensive software-based operation. And then register accesses are always more efficient than memory accesses. Registers are implemented as flip-flops on the hardware, so it has the ARM processor can directly access these values as opposed to actually asking the memory controller to go fetch something. And so as part of this, you want to also avoid register spilling. Register spilling is essentially when you have a function with like 1 million parameters. And what happens is it will put the first 4 parameters into R0 through R3, but the remainder of the parameters actually end up going on the stack, which is in memory. So you want to use registers as much as possible, so it'll be faster for access as opposed to going to the memory controller and asking the memory controller to go access the stack. Usually you can also improve the cache latency by actually giving those hint instructions I told you about earlier, where it's actually able to take consecutive memory accesses and update its cache, and then you just have to go to the cache as opposed to going to the actual memory. And then there's also use of pure functions, which don't have any side effects. So pure functions basically don't rely on, so whatever value you pass in is the only value that's needed for the function to do its work. It doesn't rely on any outside global resources and things like that. So that's what I meant by side effects. So here's an example of countdown loops. So as you can see on the left-hand side, I have a for loop from 0 to 64, and it's incrementing. So it generates add, compare, and then you have a BCC L1 at the bottom. But on the other one, you have for I equals 63 down to 0. It just generates subs and then BGE. So that's an example for countdown loops. 32-bit data types. The problem here is you can see that T3 uses a char variable versus T4, which uses an int. The difference here is a char. The GCC will actually put in a check to make sure it's between a range of 0 and 255 because it's a char, and versus using an int where it doesn't have to do that check. So as you can see here, it's doing an AND R1 with FF just to make sure it's within 255. So, any questions so far? So another one is function calls. So this is an example of the pure function that I was talking about. So here, test, you can either say return square of x times x plus square of x times x, but that will essentially result in two calls to square, so hence 2 branches. Whereas if you just say 2 times square of x times x, you have to make sure there aren't any side effects where you have synchronization issues between the two. If square were to depend on a global variable for something, then the executions of this square, the first square, would be different from the execution of the second square, and that would result in a side effect, what's called a side effect. So as long as the function doesn't have a side effect and it's a pure function, you can just optimize it by calling 2 times square of x times x. So another one is code alignment. So especially structs are very well known to cause misalignment issues. So if you arrange your variables in the struct accordingly, it will end up using less number of bytes. So you end up with a more efficient struct. And I think this is true for not only ARM, but it's also x86. But you could use a packed keyword to remove the padding, but that's dangerous because what packed does is it actually removes the padding no matter what order it's in. So it'll actually use just 1 byte, and that ends up in misaligned memory accesses, right? So in order to access car A in the first struct, it ends up actually doing a misaligned access to access, for example, car C versus in the second one. So it's always better to not use the packed keyword, but make the struct optimal ourselves manually. Does that make sense? All right. So I'll give you give you some time to read this one. So I know Charles had a beef with this. If there are any programmers with skills using butterflies, let me know. There actually now is a, what is it, Control X meta key C meta butterfly in Emacs implemented, so, which flips a bit. So, all right, so now we get to the section on writing some inline assembly using butterflies or whatever your favorite editor is. So generally, a lot of the inline assembly follows this format. This is especially, I think Benjamin from the remote site had asked about doing assembly for the iPhone. And unfortunately, I'm not too familiar with the iPhone, but iPhone development. But from what I've heard, a lot of them recommend using inline assembly in line with the Objective-C code, which is possible, and I know that it follows a similar format. The only thing I saw was on Stack Overflow, they say that all assembly functions need to start off with an underscore, but I haven't tried that myself. But you can actually use this format for your ARM assembly. So generally, the ASM directive is in your code. You just write ASM followed by the instruction that you want, but instead of using registers, you put your own variable names. And so, for example, move destination, which is result, and value, which is the operand, which is rotated by 1 bit. And so what this does is, this is actually the code that gets run, but it will assign the next available register to these variables. And the assembler does that for us. And so that's why you kind of use these variable names instead. And then you actually give the output operand list. In this case, we want to read back the register that gets assigned to result, because we want to get that value from result in our C code. And then that's followed by a colon and the input operand list, in which case, in this case, it's value. We're passing in value. And the R here, equals R, is referred to as a constraint. Equals is a modifier. I'll refer to modifiers a little bit later. And finally, the clobber list is it's apparently optional, I think, but don't quote me on that. The clobber list is essentially the list of registers that you know are going to be used up, and you don't want to touch them essentially using this code. So the assembler will try and find other registers to use in its place, essentially. So This one, we're passing, the way you pass the values into these registers. So for example, value is an input operand, and that's represented by x. And x is actually an integer that can be defined in your C code. And y is the output, and that can be another integer. So you can just say int x, int y, and then after you run this ASM command, your y will have the result from x, but you're using assembly to copy the value from x into y instead of directly using x assign or y assign x. So this is just a simplistic example that I want to use. So if you remember, I mentioned constraints. So here we're representing our variables in place of registers. But let's say you want to use, instead of registers, there are different kinds of registers you can use. So if the ARM board came with a vector floating point unit, VFU, and you wanted to do vector floating point operations, instead of using the core registers, you wanted to specify the floating point registers, which are available on that piece of hardware. You would use the F instead of the R here, equals F. And similarly, so these are all the available constraints for use in inline assembly. So generally, though, you'll be using R. So I've used this, for example, to read the CPSR value after doing a subtraction to check the negative flag. And if I want to check the negative flag of set after doing a subtraction, for whatever reason in assembly, you can do this kind of operation, but instead of using move, you use MSR or MRS. Actually, you'd use MRS to read the CPSR value into the register. So that example is in your examples directory if you want to look at it under projects example in the emulator. So that actually, you're able to read the CPSR and check if the negative flag has been set. So earlier we saw equals is a write-only. Similarly, you can have read-only and read-write. So plus is read-write, I think. I was pretty sure that was a read-only. I'll have to get back to you on the read-only modifier. But equals plus means read-write, and then ampersand is just for output. So these are used, for example, in here, the equals reference is write-only, and then this one has no modifier. I guess that means read-only, so I'll have to double-check that. So here's the example I used. So it's actually example 6. It's in your examples directory. So instead of reading the CPSR, I was trying to read the APSR just to see the flag change. And sure enough, the APSR actually gets updated. The CPSR, for some reason, in the emulator doesn't get updated. So after you run a operation that results in a negative integer, and you read the APSR, you'll see the flag actually change. So the APSR is actually a synonym for the CPSR. So they just made ARM just made another level of abstraction for application programmers to be able to read system level, registers and stuff like that. So, all right. So now that we've done inline assembly, how do we reference direct assembly code in our C programs? So as you've already seen, we can define our assembly function, which you already saw with Fibonacci. So generally, a lot of these directives are optional. So here, all I'm saying is the syntax is using unified assembly language, which is what the ARM v7 follows. And the reason these come in handy is so that if you're running the same code on older, or if you were to run this on a newer architecture, it would preserve the features of the older architecture. And generally, ARM tends to make them backwards compatible, so you'll be able to use the same piece of code. And this also specifies the architecture. And since it's thumb mode, it's always aligned to 2 bytes. So these are actually optional because you can specify those with GCC options. And then finally, to declare a function, you say .global my work. It's a global method. And then you say the type of my work is function. And then you put your code here, and then you end with .size my work minus my work. So this actually calculates the size of your method. I'm not really sure why you need it, but I found that things don't work if you don't have that in there. And finally, you end the code. So it starts with .text and ends with .end. So this is sort of your text section, if you remember the ARM ELF syntax. And finally, to compile your code, you would write gcc-c-o, the object file, followed by the assembly file. And when you want to compile this object with your C code, you would say gcc-o, the binary name, followed by the object files. And as long as in your C code you've referenced an extern int, that method with all the argument declaration, I guess, the function declaration, you just have to put it as an extern, and when GCC compiles, it will link the two together. Any questions so far?